Okay, what we're going to do here is we're going to talk about water, the functions of water. We're going to talk about acids, bases, salts, and buffers generically. We're not going to get into huge things because we're going to be doing some experiments in lab about acids, bases, and buffers. And we're going to talk about the effects of acids and bases on a solution, namely its pH. And we're going to talk about the pH range of blood, which is just a couple of numbers that you should just remember. Yeah. All right, so water. So we know what water, the formula of water, the chemical formula, it is simply H2O. H2O, that's the chemical formula. And its structure is an oxygen bound to two hydrogens. Remember, because those bonds between oxygen and hydrogen are polar covalent bonds, the charge on oxygen is slightly negative and the charge on the hydrogens are slightly positive. Okay? So now, a simple molecule. It is really a really simple molecule. And it does a lot for us. Okay? Among those things, water, okay, is the solvent in which most chemical reactions of the body take place. One thing I like to tell students, just so they can simplify the importance of water, and it's generic, it's in an overstatement, and there is always counterexamples, but for us, it will pretty much hold through, is if your body cannot dissolve it inside of water, into water, it can't really use it. I mean, that's how important water is. Okay, so if it's not water soluble, you can't get it to dissolve in water somehow, you can't use it. Okay? Water is approximately 2/3 of lean body mass. Okay. Notice here I put this lean body mass. So if you have somebody who is within the normal 3 to 6, well, I'll say to 10. If you don't worry about percentages. You have somebody who has normal body weight. So like this 70 kilogram male, 2/3 of their body weight is water. Okay? When you get heavier, when you start to add more adipose on, more fat onto the body itself, the water ratio actually changes because adipose tissue doesn't have much water in it. And so you got to think, well, where's water inside of the body? It's pretty much everywhere. Most of the water inside of your body is what's called intracellular. It's inside of the cell. Okay, most is intracellular. Okay, so the fluid inside of the cell is where most of your body fluid actually is. Okay, then you have the extracellular. Okay, and this is between the cells. And then we have the intravascular, which is basically the fluid portion of your blood. Because what we're going to see when we talk about blood has actually got two parts to it. It's got the formed elements, or the cells, and it's got the liquid portion, the plasma. The plasma is predominantly water, and you got crap dissolved inside of the water. The plasma by far is the greater component. So water is a very, very dominant in all parts of our body itself. Okay, even the solid parts of your body. So like people think that bones are semi-solid. Okay, but bones are cells and extracellular fluid. And cells and extracellular fluid, a lot of water, even inside bones and cartilages. Okay, so another thing that's amazing about water is it's got a high heat capacity. It has a high heat capacity. And what this means is it takes a lot of energy. It takes a lot of thermal energy in order to actually raise water temperature-wise. And you notice this if you've ever tried to sit and boil water. sit and boil water. So the reason it takes so long to boil water because you have to put a lot of energy into that water in order to make it raise in temperature. And the reason for this is because of a special bond that's found in water called the hydrogen bond. Okay, the hydrogen bond. Now, if you've taken a biology class before, beginning Bio 101 of any sorts in college or in high school, you talked about this. And this is one of those things that I understand if you're just like, do I need to know this to pass a test? And somebody probably said no, and you just forgot it. I get it. It makes a lot of sense. But the hydrogen bond is actually really important when it comes to water, itself. So if we look at the structure of water again, okay, we have that slightly negative oxygen. We have these slightly positives on hydrogens. Okay. Now remember, water, it's got an ice. It can exist as ice. Water can exist as a liquid, and water can exist as a gas and water vapor. Okay. Inside of us, majority of the water is actually in the liquid state. It's in the liquid state itself. It's never inside of us. Normally, it's never ice. Okay, unless there's something gone terribly wrong. So if you look at the way this water is actually going to line itself up, you're going to have oxygen next to these hydrogens, and then this negatively charged oxygen is going to actually want to hang out with the positively charged hydrogen on another water molecule. They're not going to bond to each other. There's going to be no physical bond there. But you got this slightly positive, slightly negative, and what that's going to do is there's going to be a little bit of an electromagnetic attraction there. That positive is going to attract that negative, and there's going to be a little bond. I don't like the word bond because there's going to be an attraction there, and they're not going to want to separate very easily. That's the best way to say it. And this attraction between the polar hydrogen and the polar oxygen, it is called a hydrogen bond. It's called a hydrogen bond. And when you have that hydrogen bond there, it means it takes a little bit more energy to break it apart. It's like when you have two magnets stuck together, it takes a little bit of force to break them apart, but once you break them apart, they'll move apart easily. Same thing happens in water. And so if I want to go from a liquid state where the molecules are close together and they're moving around to a gaseous state, at 100 degrees Celsius, where the molecules will escape from the liquid and go into a vapor, I have to break these hydrogen bonds. I have to get enough energy into those to break the hydrogen bonds and get some of those molecules to escape off into the air. Okay, and what prevents that from happening is the hydrogen bond themselves. Okay, so I don't want you to confuse hydrogen bond with a covalent bond and an ionic bond. Okay, so ionic bonds and ionic bonds and covalent bonds are between atoms, themselves. Hydrogen bonds are between compounds and molecules. Okay, there's no direct electron sharing in a hydrogen bond. Okay, or no electron stealing as in the case of an ionic bond. Okay, what a hydrogen bond is just the positive charge is attracted to that negative charge, and what it does is it pulls those molecules a little bit closer and gives them a little bit of strength. Okay, a prime example of hydrogen bonding in water is this thing called surface tension. Okay, if you've ever been on the river, if you've ever been or seen water, and if you've seen bugs crawl along the surface of the water, okay, the reason that the bugs will just are able to go walk on the surface of the water is because of the surface tension of the water, and that is predominantly due to hydrogen bonds. Okay, hydrogen bonds hold those molecules together so closely and so well that insects can walk on the surface of the water. Or if you've ever filled a cup with water too high, and you can see that the water actually comes above the rim of the cup. And the reason that is possible is because those hydrogen bonds give a surface tension to the water. And what that does is it gives it a structure almost. And if you've ever wondered, why does ice expand Okay, if you look at pretty much every other liquid every other liquid on Earth, when you take the liquid and you freeze it, it actually contracts. It actually gets smaller. Okay, but in water, if you take a liquid and you freeze it, it actually expands out. And the reason is the hydrogen bonds. The hydrogen bonds actually have an expanded crystalline structure. Okay, the hydrogen bonds, keep the molecules at a certain distance apart from each other, so it causes the ice to expand outwards. So that's what a hydrogen bond is. Okay, that's high heat capacity. It was a very long aside on heat capacity, but the reason we have a high heat capacity is because of the hydrogen bonding. Okay, and one of the last things that water does for us in our body is lubrication. Okay, lubrication. Okay. All of these other ones, we're going to talk about each one as we go through in the course. We'll talk about where water is a lubricant and things like that. But we're going to deal with pretty much the solvent aspects of water for the rest of what we're going to talk about today. Okay, so now in order to understand what a solvent is, we have to talk about what a solution is. A solution. Now, a solution is nothing more than a mixture of two or more substances. Okay, that's it. Two more substances. Okay, in a solution, you have this thing called a solvent. You have this thing called a solvent. We already said that water is a solvent. It is a solvent. Okay, so I wrote it in red, so because it's important. Okay, and a solvent is simply the thing that dissolves. Is the thing that dissolves, or which dissolves, however you want to do it. And then another part of the solution is we have the solute. The solute. And what the solute is the thing that is dissolved. Okay, so pretty simple, right? Okay, so example. If I have a glass of water, here's my glass. Let's put some water in it. I'm going to say this is H2O, water. And we're going to put salt. We're going to put salt. We got just a clump of sodium chloride, table salt, NaCl. Now if we take that and we put it in there, and you've all done this at one time in your lives, sodium chloride inside of water, and you stir it up, and eventually what happens is the sodium chloride, ta-da, magically disappears. Okay, it doesn't disappear, it actually gets dissolved into the water. And what I have is a water sodium chloride solution. It is a solution. Okay, so now what things will dissolve in water? What things will dissolve in water? And it's pretty easy. The things that will dissolve in water. Okay. Ions and polar compounds will dissolve in water. Okay. Water and ions and polar compounds will dissolve in water. And how they do this is they typically dissociate. So if you look at sodium chloride, NaCl. So now when you look at NaCl, you look at table salt. Take some table salt and put it on your hand, and it's actually in a crystalline form. It's got this whitish color, and it looks like little crystals. And if you put it in water, what actually happens is the sodium and the chloride, they break apart from each other. Okay, dissociate. That's called dissociate. Okay, so that's just a fancy way of saying they separate. Okay, so it's going to go into the positively charged cation. Sodium is the positively charged cation, and chloride is going to be the negatively charged. Okay, so they dissociate into their relative ions. And then what's going to happen in water? You got the oxygen. Okay. got the partially negative charge on oxygen. You got the partially positive charges on the hydrogen. This sodium, red is important. This sodium here is going to be really attracted to that. So the sodium is going to come hang out next to the oxygen. And this chloride, let's make it a dark green. This chloride is going to be attracted to the negatively charged hydrogen. Sorry, the positively charged hydrogen. The negatively charged chloride is going to be attracted to the positively charged hydrogen, and they're going to hang out like that. And that's what happens when things dissolve. When things dissolve on the water molecule itself. That's what happens. Ions dissociate, and they go to their relative sides of the water molecule. Okay. Now, you've heard the term electrolyte. Now, water itself, pure water, if you have water by itself, it typically does not conduct electricity. Okay, does not conduct electricity. If you add a solute that grants, it's like a gift, water the ability to conduct electricity, that solute is an electrolyte. Okay, that's the definition of an electrolyte. Now, when you listen to like all those Gatorade commercials and stuff like that, like vitamins and minerals and electrolytes, vitamins and minerals are electrolytes. Okay, they will give water the ability to conduct electricity. So that's what an electrolyte does. It gives water the ability to conduct electricity. Okay, that's what an electrolyte does. Okay, so don't let anybody tell you it's more complex than it is. Okay, so basically when you dissolve a salt, any kind of salt inside of a water, you're adding electrolytes. That water is going to be able to conduct electricity. Okay, all right, moving on. Okay, so we've already established that water is polar. Okay, if a substance dissolves in water, it is hydrophilic. If a solute dissolves in water, it is hydrophilic. Okay, and this means it is water loving. So it loves the water. Loves the water. It is hydrophilic. If it does not, if a solute does not dissolve in water, it is hydrophobic. And this is water fearing. So it doesn't like water. Okay, so you've seen hydrophilic and hydrophobic solute before. So whenever you sugar water, you drunk a lot of too. Pepsi, hydrophilic. Salt water, hydrophilic. The typical hydrophobic that you're going to see, and one that we're going to see quite often, and it presents a special problem to physiology, is fats, oils and water don't mix. You've all heard that. Oils and water don't mix. Oil and water doesn't mix. And that's true. Okay. They do not mix with each other. If you take oil, you put it in water, you shake, what you'll see is these little globules of fat that are floating in the water, and eventually they're all going to rise, and the fat is going to be at the top of the water, and the water is going to be sitting down at the bottom. And the reason is because lipids are less dense than water. That's why it floats on top. Okay, but they will not mix normally. Okay, so The general rule, you're like, well, how can I determine if something is going to be hydrophobic or hydrophilic? Just by looking at it. Okay. So I already told you hydrophilic ions. Okay. Ions. So basically charged particles and polar compounds are typically going to be hydrophilic. Now, in general, what are going to be my hydrophobics? Okay, this is pretty simple for us. Our fats, oils. Well, oils are a term of fat, but that's it. And non-polars. Fats, oils, and are typically non-polar compounds. Okay, so solutions. We talk about water being, one of the universal solvents, and then things that are dissolved in it, solutes. What things will dissolve inside of water, what things won't dissolve in water, and how water attaches to things, with or in when we're in water. Okay, so now we're going to talk about types of solutions. There's only two you really got to know. Okay, so we have these things called colloids, types of solutions. Okay, so we got number one. Okay, this is a colloid. Okay, and basically this is a solution of large molecules. Okay, and the way to think about them is gels. And once you get a colloid, you can't undo a colloid. Okay, so once you put the solutes inside of the solution, you can't get them out. Okay, solutes cannot be filtered out. Okay, one of the best colloids that you've ever seen is Jello, Jello. Okay, so you put that little packet inside of the water, you stir it up, put it in the refrigerator, and then it becomes a shaky thing. Now, there's no way you can filter that out ever. You can't get that package out. It's not like salt water, where if you dissolve salt inside of water, and if you leave it out long enough, the water will eventually evaporate out, and you'll get salt crystals in the end. Okay, salt water is not a colloid. A colloid, you can't filter it out. It's done. You're basically changing the structure of that. And then we have suspensions. Okay, and so this is where the particles aren't technically dissolved, they just float around in the water. Okay, so the particles float in the water and eventually settle. So the best example of this is sand. You ever put sand in water? You shake it up. You can actually see the sand, float in the currents of the water itself. And then if you leave it alone, what happens is the sand will settle down to the bottom. Will actually settle down to the bottom of the container. Okay, that's one you've seen, commonly. Another suspension that I want you to remember. It's a very important suspension, is the blood. The blood is a suspension. So when you actually take blood, those of you who are phlebotomists or have taken blood before, okay, if you leave it in the tube untreated, what's going to happen is the red blood cells, all the foreign elements, so basically the red blood cells, the white blood cells, and the platelets, are all going to sink to the bottom. Okay, and then the heavier components are going to, the lighter components, then that are going to sink to that. And then what you're going to do is you're going to have this yellowish liquid, the plasma at the top. Okay, because blood is a suspension. It is a suspension itself. So that's what it is. So it's really not dissolved. They're really not being dissolved. They're just floating around in the water. And if they stop moving, and let gravity do its work, gravity is going to pull. It's going to pull the heavier objects down. It's going to keep the lighter objects at the top. Okay. So those are the two I want you to remember. Okay. So concentration. When we talk about solutions, we have to talk about concentration. So concentration. Oops, let's get out of red. Concentrations. A concentration is the amount of solute in a solvent. Okay, it's how much stuff I have dissolved into my solvent. Okay, and how it's typically written, it's written as this thing called mole per liter or milligram per milliliter. Okay, so now this word mole, it's got a very significant definition. Okay, a mole is the number of atoms. Okay, and that means number, not hashtag. Okay, so don't try to look that up. It's not going to get you anything. Okay, it's the number of atoms in a sample. And it represents this number called Avogadro's numbers. Sorry, Avogadro's number. Which is 6.022 times 10 to the 23rd power. So when you have a mole, when you have one single mole of a sample, of an item, let's say we have 1 mole of sodium chloride, NaCl. So 1 mole of NaCl. That means I have 6.022 times 10 to the 23rd NaCls in that sample. Okay, that means I have 6.022 times 10 to the 23rd sodiums. Then I have 6.022 times 10 to the 23rd chlorides. Okay, in that, and that's what it is. So if that is in 1 liter, if I've taken that many sodium chlorides and dissolved it in 1 liter of water, the concentration is 1 mole per liter. 1 mole per liter. So now if I take that liter and I put it in half-liter containers, it is still, the concentration is still 1 mole per liter, because it is the amount of stuff I've dissolved over the volume. Okay, so as long as I equally distribute up the volumes, the concentrations will stay the same. And with that, I think we're gonna stop there, because we're bumping up against the half-hour mark. Okay, so the next one we're going to talk about acids, bases, and buffers.